Okay, welcome everyone, and thank you for joining this training session on functional safety. This training is part of the Reboot Skills project, which in turn is part of the Digital Europe program. So it's a European funded project and curriculum. So our goal is to develop a skill talent pool of European digital experts by offering you free courses on AI, robotics, IoT, and cybersecurity. We mainly target SMEs and specifically employees with some background in engineering, but also in unemployed people. And so these courses are targeted towards you, or we hope that you fit the profile that I just mentioned. They typically situate in awareness, discovery, or intermediate levels of difficulty. So we are Flanders Make, but we are not the only organization developing these courses. Courses are actually being developed throughout Europe by other partners as well, such as the University of Oulu in Finland, Limerick, and together with partners in Italy and Sweden as well. So back to this course, functional safety. It focuses on the functional safety life cycle and how it impacts the design and the operation of any robotic system. Ms. Neiroza Badr and Mirjam Verschuren, also here present, of course, will be your teachers for today. Neiroza is working as a research engineer and she has a background in reliability, quality, and innovation as an industrial engineer. Miriam is also a research engineer and she's working in several domains, going from logistics to agriculture to automotive. So together they will teach you the fundamentals of functional safety. And after this training, I invite you to check out our event page on the Flanders Make website or the Reboot Skills LinkedIn page to see what other trainings we have in store for you in the coming months. So thank you again, and I'll leave the word to Neiroza.
Yes, thank you, Laurent. So hello, everyone. Thank you for joining. Welcome to Functional Safety for Autonomous Driving Systems training. My name is Neiroza Badr. I am Functional Safety Research Engineer. I work for Flanders Make, and I will be your instructor today. So this webinar will take 2 hours. We will start at 1:05 and finish at 3 o'clock, and there are no breaks for this training. So before we start, I invite you to write your name, profession, and for which company you work on the chat. And also, I would like you to answer this poll in which you will tell me how you consider yourself in functional safety. So I will launch the poll for you. So please feel free to answer. I can see that most of the attendees are beginners. Some of them are professional. Yeah, so I think that this is the right training for you as it is training for awareness. So now I would like to cite the instruction for this webinar. So this webinar will be recorded. So for those who do not agree, your cameras will be automatically switched off and your microphones will be muted as well. At the end of the webinar, there will be a debrief where you can ask your questions. So if you have any questions or comments, please drop them in the Q&A section. And last, there will be small quizzes and surveys. So I invite you to actively participate during the whole training. And now for those who have just joined, so welcome you again and thank you for joining this webinar about functional safety for autonomous guided systems. My name is Neiroza Badr and I'm a research functional safety engineer and I will be your instructor today. So here another question is please write your location so that I can see from where this webinar is being followed. I will launch the poll. So feel free to answer. I can see people that are from Belgium. We have Finland, Turkey, France. We have diverse audience, which is good. Thank you for your answers. So the level of this training is awareness, and by the end of this webinar, you will be able to do 3 things. First one is to understand the relevance of functional safety. The second is to be able to recall functional safety process that is necessary to assess and improve your product and process design. The third one is to be also able to recognize some of the functional safety methods and key parameters that are necessary also to assess and improve the product and process design. So before we get started, I would like to highlight on some key facts and statistics. So according to Occupational Safety and Health Administration, every 3 days a person gets killed in forklift accidents, and many accidents are either crashes, flying objects, or cutting. So now we're going to see how we can prevent these accidents and help design safer systems with the implementation of functional safety process. So now let's go through the agenda of this webinar. First, we're going to start with an introduction to functional safety. We're going to see what is the purpose of functional safety, what do we mean by functional safety, and then we're going to deep dive at their general phases. So we're going to see the functional safety process, how it is implemented in analysis phase, how it is implemented in realization phase, and how it is implemented in exploitation phase. Last, we're going to conclude and do a small summary for all what you have seen or what we're going to see. And also we're going to go through the next steps. First, we're going to start with the introduction to functional safety. I'm sorry. So we're going to see what is functional safety. What do we mean by functional safety? Functional safety is a systematic approach, and by this I mean an approach that is conducted through the design life cycle of the system. In this approach, we use a set of principles and techniques which we're going to see in details in the following slides, in order to ensure that a system is able to operate without causing any injuries. So what you need to remember is that functional safety is the aspect of safety that deals with ensuring that an electronic, programmable electronic system operates correctly and predictably by controlling the failures and therefore preventing from danger. So here in this slide, we can see in the figure on the right, the primary causes of failure or incorrect functioning of EEPE systems. They come from the specification. Through incorrect specifications, they can occur in design changes, in implementation, they can also occur in operations and maintenance and repair. On the left, we have other possible causes for incorrect functioning. So we can see random failures mechanisms. So they occur predictably and are due to inherent limitations in the materials or components used in the hardware. For example, electronic components failing due to aging or other natural like multiple wear and wear. We have systematic failures, hardware failures mechanism. So unlike random failure mechanism, they occur predictably and are usually due to design flaws, manufacturing defects, or issues in the operating environment. For example, a design error in a circuit that leads to overheating under certain conditions. We can find also software errors such as coding errors, design errors, configuration errors, and we can also find common cause failures. It is when two or more components that are supposed to operate independently fail together due to the same root cause. So they are particularly dangerous because they can defeat the systems built in. For example, if a redundant sensor in a system fails simultaneously due to the same shared root cause, this can cause the system to lose its ability to detect and respond to hazardous conditions. So functional safety is a systematic development approach to minimize the risk of system failure resulting into harm. It interferes in each phase of the design lifecycle: the concept, production, development, operations, recycling, and in each phase, you must know that failures may occur, and the earlier functional safety is implemented, the earlier the prediction of failure is possible, and therefore risks may be mitigated and controlled. So this could help to minimize the risks, but also could help minimizing the costs that are resulting, for example, from maintenance. So now I have a question for you, and I would like you to answer in this poll. Why do you think that functional safety is important? I will launch the poll right now. So I need you to answer and think of possible things that could make functional safety important in maximum 2 words. I can see liability, concerns, safety of workers, injuries, prevent injuries, protect humans, prevent hazards, that's right. Productivity, safety of people, that's right. Yeah, it is an interactive. Yeah, I think overall you thought of, yeah, injuries, operation for users, most for protecting humans, safety operations. That's correct. That's good. So functional safety is important for many reasons. As most of you have answered, it is used to avoid harm, but also be aware that it has important impact on money. So there is the legal aspects where you are faced to standards and regulations before putting your product in the market. So there is the liability aspect that is very important. So you won't be able to put your products in the market and you will have economic losses and also an unreliable product and a product that causes damages to health of person caused by malfunctions of the product would ruin the reputation of the manufacturer and you will be faced to no demand with loss of production. So all these aspects are very important besides avoiding harm. In the next slide, we're going to see the overall objective of functional safety. So the overall objective of functional safety is to reduce the risk of an equipment under control to tolerable levels by means of EEPE systems and other measures. So the necessary risk reduction is to have no risk or tolerable risk. So no risk is like the perfect and ideal thing, but you cannot have it because there is nothing that is perfect in this world. So at least you will try to reach it to a tolerable risk as possible. So you start from a risk to a tolerable risk, and for that you need to implement measures and safety-related systems, EEPE systems. So now we're going to see some of functional safety domains. Functional safety is implemented in many domains, such as automotive vehicles, robotics, agriculture, nuclear, railways, medical devices, and other domains. But in this training, we're going to try to focus on the robotic domain. And as we say, there are domains where it is applied. So for each domain, there are standards and principles that are dedicated to the implementation of functional safety in order to have a liable product at the end. So we are going to see applications of functional safety on robotics, and we are going to see some of the methods from ISO 13839 for machinery and also ISO 3691 for driverless industrial trucks. So all these safety standards, they come from the mother standard, which is IEC 61508, which is the functional safety standard for industrial applications. Now, I would like you to do a small quiz. Now that we have seen the meaning of functional safety, why do we need functional safety? So I would like you to answer this quiz. I will launch it now. And I will give you 30 seconds to try to select the correct answer. So what is functional safety to you? You have two options, A and B. I have a very interactive audience today. People are answering on the chat and also on the quiz. Yeah, so most of you have the correct answer, which is A, systematic approach using a set of principal techniques to ensure the ability of systems to operate without causing injuries. B is not the correct answer because it is a systematic approach. It can be used to ensure availability, but we can be sometimes forced to, due to the safety aspect, we can be faced to like switch off some of the equipments, which could lead to an unavailability of the system to operate in order to be in a safe state. So good, congratulations to most who have answered correct. That means that you're going on the good path. Now let's go back to our presentation. And let's go to the next chapter. So now we're gonna deep dive in the functional safety process. So we're going to see how functional safety is implemented in the life cycle of a product design. So here, the generic functional safety life cycle goes through three phases: analysis phase, realization phase, exploitation phase. And in each phase, we have steps of this process in which we're going to implement our functional safety. So first, we're going to start by analysis phase. So in analysis phase, we build our functional safety concept. So we start with the system definition, then perform the risk analysis, and finally, we specify the safety requirements. First step is system definition. In system definition, we aim to define these four elements: functional concepts, operating mode and concept, the preliminary architecture, and last, operational situations. The purpose of system definition is to have a clear understanding of the overall system. So, well-defined system provides detailed description of the system's boundaries, the components, and their interactions. This helps also identify what is part of the system and what external factors that might affect its functionality and safety. It helps also to identify potential hazards early in design phase by clarifying how different parts of the system work together, and the clear system definition ensures always that safety requirements can be accurately derived. So for these four aspects, these are some of the questions that could help you to have a complete and exhaustive system definition. What are the system functions? We think of what are the parameters or elements derived from these functions. We think of what are the operating modes. We think of what are the operational situation and also what could be the malfunctions. So here, I would like you to do together an example of system definition on auto-guided vehicle, AGVs. So in our practice, we're going to do the system definition. So we're going to have three tables, which we're going to try to fill in some examples. So on the right side, we have the elements of structure. So this is not an exhaustive example, just a summarized one for our assignment. So we have the logic of the AGV, we have sensors, speed sensors, steering position, we can find left position, other sensors, and we have the actuators part, like drive motor, the brake, the steering motor, the forklift motor. So on our left side, we have table 1, in which I would like you to fill in just to have an idea on what could be the functions for this AGV, what could be the parameters of the function, and what could be the malfunction of this function. So it could be like no function, it could be like loss of function, degraded function, function. So for example, here we have function drive-in function for the AGVs. What could be the parameters? So the AGV could be driving either backwards, forwards, for example. Malfunction, it could be like driving with high speed, like we could have an overspeed driving malfunction. And the second table is we're going to try to define examples of operational situations. Like in here, think that AGV is driving between racks with high or low speed in a manufactory, for example. And here, the possible modes that we could define, like being on off mode, maintenance mode, manual mode, automatic mode, charging modes, quite similar to like in the automotive vehicles, for example. So here, what I would like you to do is to take a piece of paper for like 30 seconds and try to think of an example of function, what could be the parameters of this function, and what could be one malfunction of this function. And I would like you to share it, to raise your hand after, and one of you could share it in the chat. So I will give you, let's see, 1 minute. Could be enough. Sorry, I will keep the slides for you so that you can see. And if one of you have thought of an example, we can discuss it together from the chats. Yeah, so we have one participant, lots of functions left in, that's correct. Parameters up and down, yeah, that's correct. Also, malfunctions left in erroneously down instead of up, yeah, that's of degraded function, operational picking up an object in the field. That's actually correct. I wasn't expecting to have this interaction. Does anyone have another example that could be willing to share? But at least we can find that you are on the right path. So congratulations for your correct answers. That could be an example of a system definition. Now we're going to see another exhaustive example of answers on system definition on AGV. I can see, yeah, parameter function, malfunction breaks failing. That's also correct. Good. So we have seen left as function, up and down, which you have taught, unexpected down and up, which was correct also that you guessed. We have others like localization, obstacle detection, the charging, and also operational situation. We can also have like driving at the end of corridor, pick up pallets at pickup points. So this is an example of system definition in AGV. So it's more simplified, but of course, like it is complex. And with a complex architecture, we can find much more complex functions and malfunctions and parameters and also operational situations. So well done, everyone. Well done for the answers. And yeah, it was correct. Now let's go to perform a small quiz. So I need you to tell me or think of what could be the elements needed in system definition now that you've done the assignments. So I will launch the poll for that. In maximum 2 words. So let's see if you remember some of the elements of the system definition. Operating modes, I can see function, parameters, that's correct. Operating modes. Preliminary architecture, that's also correct. Yeah, so most of you have guessed the correct answers, the correct elements. Congratulations for that. Now let's go to the other step of analysis, which is the risk analysis. So before we go and deep dive in risk analysis step, I would like to cite some terminologies and classifications of failure that are from the ISO 13849 for machinery that we're going to need in this next step. So what is a risk analysis? So risk analysis is the combination of machine limits, the specifications, the hazard identification, the risk estimation. So it's the whole process. The hazard is a potential source of harm. A hazardous situation or event is a circumstance in which a person can be exposed to a hazard, and safety function of a machine is in which failure can result in an immediate increase of the risk. So functional safety is a build-up process. First, we start by defining the overall system we have, our functions, the architectures, all the elements we need for the risk analysis of the system. So next step is to identify the possible hazard related to these functions and elements, and this by listing and identifying all the possible situation analysis. And after that, we think about all possible hazardous events that could occur due to these hazards in specific situations. It comes the assessment and the classification of the risks that we're going to see in the next slide. So how classification is performed according to ISO 13849 standard for machinery. And also the purpose of this risk analysis allows the creation of functional safety requirements. So required performance level. Required performance level is a measure used to assess the reliability of safety-related systems. It is used to determine the required safety performance. Performance level is expressed using letters from PLA to PLA, where PLA is the lowest risk reduction capability, and PLE is the highest risk reduction capability. So each PL is defined by three factors. We have severity of injury, so how severe the injury or harm could be. For example, here on the left, it can vary from S1 slight injury to S2 referring to serious injury. The second factor is the frequency of exposure. So how often the hazardous situation occurs. Could be a low frequency, like seldom to short duration as F1, and high frequency as frequent to long duration for F2. The last factor is the possibility of avoidance, the possibility to avoid or mitigate the hazard once exposed. So it could be either possible as P1 or hardly possible or even impossible as P2. So what you need to remember in this slide is why we need the risk classification. This graph on the left shows you how much good your system needs to be depending on the importance of the risk. So if you have a high risk, make some effort on your design. High risk requires a PLE. Here is the most effort you need because you have a higher risk. And A is the less effort you need because you have low risks. So here we're going to do a second assignment and try to think of hazardous situations, hazardous events for cobot. Like here, we're going to see, I already made an example for forklifts. For example, possible hazardous situation could be driving between racks at max speed, loaded, personal on pads. This hazardous situation could cause a hazardous event, so the forklift hits a person, heavy injury. Another example could be for the forklifts, like we have picking up and lifting, as we saw as an example of function. So it could be dropping a pallet at drop location, but we have a personnel present. So this is a hazard, could be a possible hazardous situation. And the equivalent hazardous event to this hazardous situation could be the forklift drops the pallet on the person. So here, I would like you to think of an example of hazardous situation and also what could be the hazardous events of this hazard situation on a cobot. So for people that are new to the cobots, cobot is a collaborative robot that is intended to work hand in hand with employees. So they tasks along with the employees, such as picking, helping workers, focus on their tasks. So they can have, like, for example, a robotic arm that helps on the picking up and everything. So I will leave you same as the previous example, 30 seconds to try to think of hazardous situation, hazardous event. And please feel free to share one of your examples on the chat, and we're going to discuss them together. So we have one of you that said that hazardous situation could be cobot pushes into operator. That's correct. Another one said cobot don't detect a person. Collision as hazardous event. That also correct. Cobot hit a human hand. That's correct. Even slight injury. Yeah. Well done. I think he got it right. Another one, hazardous situation. Cobot might misguide the operator and cause a failure. Yeah, I think that's overall all of you got it right. And you start of thinking of possible hazardous situations. So now you must know that you are starting to build your risk analysis. And I can see that in this, you are taking into account the system definition, the functions that could be possible. And starting from that, you think what could be the hazardous situations. So I congratulate all the participants. Well done for your job. You've guessed it right. Now let's see some of the examples. So as one of you said, so it's nearly drop a workpiece with personal presence. Yeah, collision, it's heavy injury. Some of you said like robotic arm also. When it's at max speed and we have personal presence, it could lead also to a heavy injury hitting person. So yeah, that's the overall correct answers of all of you. Thank you for participating and well done so far. Now we have seen the risk classification, which is one of the safety aspects. In this slide, we're going to see other parameters that helps assess the products and helps improve the robustness and the reliability of the product. Sorry. So there are other three safety parameters that we need to consider. Also, mean time to dangerous failure for reliability of the component. We have another safety parameter, which is diagnostic coverage for systems' ability to diagnose dangerous faults, and also another parameter category it's on the architecture of the component of system. So in the next slides, we're going to see in details why do we use each of these parameters. So the first parameter is the mean time to dangerous failure, MTTFT. The mean time to dangerous failure means the time to dangerous failure that represents the expected operational time before a dangerous failure occurs. So it is a measure of reliability and is used to estimate how often failures might occur. It is also a safety parameter that is used at the end to have the performance level. So it is expressed into years, into ranges from low to medium to high. So what you need to understand is that the higher the MTTF of the component is, the greater the overall of the system's reliability is. In the next slide, we're going to see the second safety parameter, which is the diagnostic coverage. It is the percentage of dangerous failures that are detected by the system's diagnostic mechanisms compared to all possible dangerous failures. So it measures the effectiveness of the system fault detection capability and is also a safety parameter that is used to predict the performance level. So here it is expressed in ranges. So it goes either we have no diagnostic coverage to low to medium to high diagnostic coverage. So the third safety parameter is the category. The category, it describes the system architecture. So it determines the system's resistance to faults and the system's ability to maintain safety during and after faults. So here we have category B and 1 that are categories where the occurrence of faults can lead to loss of safety functions. The difference between category B and category 1 is that in category 1, we have the probability of the occurrence of fault that is lower than in category B. So the architecture overall is we have a logic, we have an input device, and an output device. In category 2, faults can be detected by tests, and the loss of subfunction is detected by tests. So for category 2, the architecture is more different than category B, and we put a plus effort than in category B for detecting faults. For example, here we have test equipment and output of test equipment and small monitoring. In category 3 and 4, a single fault does not result in loss of the safety function due to the monitoring, and the fault detection. The difference between category 3 and category 4 is that in category 3, if we have the accumulation of undetected faults, this can lead to the loss of safety function. But in category 4, there is detection of the accumulated faults. So it is detected in time to prevent the loss of the function. Another information you need to know is that in category B, the maximum achievable performance level is B. For category 1, the maximum achievable performance level is C. For category 2, the maximum PL achievable is PLD. For category 3 and 4, the maximum PL that is achievable is PLE. So here, what you need to understand is much effort you make on your architecture design, the most reliable category you have on your architecture, which helps on the PL level. So here the PL is estimated by the estimation of the following aspects that we have seen: the architecture by assigning a category to the system, the MTTFD, the diagnostic coverage, and also there is another aspect that is common cause failures also. And these are all quantifiable aspects. So there are other aspects that are qualitative, such as the behavior of the safety function under false conditions and other examples. So here in the slide, we see on the left in the graph, the performance level desired that we need. So it varies from the lowest to the highest. And here we have, depending on the categories, depending on the frequency of dangerous failure, and depending also on the diagnostic coverage that we have, we can achieve a certain performance level. So the match in this slide, what you need to remember is that if you are faced to a high risk, you need to put efforts on your design, like on your diagnostic. You need to have at least category 3 or category 4. You need to have from medium to high MTTF. You need to have from medium to high diagnostic coverage for your system to be more reliable. Now let's go to another method that we can use to achieve this reliability. We have seen in the previous slides the bottom-up approach by defining the system and identifying the risks and hazards. Now we are going to see a complementary risk analysis, which is the fault tree analysis. It is a fundamental tool in functional safety to help engineers and also safety professionals to identify, understand, and mitigate the risk associated with system failures. So it is a top-down approach that provides the understanding of how components failures can lead to system-wide hazards, and by this you can implement safety mechanism to reduce the risk. So first, you define your top event, which is the unwanted event, the failure, the primary system failure, and then you break down the causes of the top event using combination of an example here or AND gate. There are other gates that you use. And also by this, you identify intermediate events that could contribute to the failure, and you break down till you get to the root causes in basic events in which there is no possible other level that could lead to a failure. So I know that it's a lot of information. That's why I prepared small example just to try to visualize a little bit what do we do exactly in FTA. So here is an example of forklift TGV. For example, our top event will be the primary failure to stop before obstacle race. We break down by using logic here, like OR logic, into intermediate events, and by this we take into account the architecture of our product. So for example, a sensors that fail to detect obstacle could lead to failure to stop before obstacle. Actuator failures could lead to our top event. PLC failure could also lead to failure to stop before obstacle, and also a communication in failures. What we do next is we try to break it down to the root causes. So we're going to see in the architecture of the sensors, and we're going to see the possible failures. For example, here we have the obstacle sensor failures, we have the localization sensor failures, the steering position sensors. For actuators as well, failure to brake, we're going to see on the motor, the relay failure, and we're going to deep dive in each level by intermediate events till we get to our basic events, in which there is no other possible level of failures that could this failure. For example, here, damaged wiring for relay like contact wear. So this is a small example, so it's a bit summarized and not detailed. Now we're gonna go through another quiz to see if you memorize some of the key safety parameters. I will launch the poll right now. So think of what are some of the safety parameters in maximum 2 words. I will launch the poll. There you go. You have 15 seconds. Try to think. Maybe you can recall some of safety parameters that I've just explained. Mean time to failure, reliability. That's correct. MCCF. GC diagnostic coverage. That's correct. Performance level, correct also. I think you overall managed to recall some of the safety requirements that were explained in the previous slides. Well done for you. Category, that's also correct. MTTA, diagnostic coverage, yeah. I think most of you have managed to recall all of these parameters. So well done again for your answers. So this was our third quiz so far. Thank you for your interaction. Now we're going to the other aspect in or the final step for analysis phase, which is safety requirement specification. So in the V life cycle, the objective is to specify the functional safety requirements. The input to this step is to start with the system definition and the preliminary architecture. Then we perform a risk analysis by using some of the functional safety techniques and principles such as hazard analysis, risk assessments to get the safety goals and hazards, and then perform a fault tree analysis as a complementary analysis in order to derive functional safety requirements and then derive functional safety requirement taking into account the architecture and the technical requirements to be able at the end to have a full specification of safety requirements. Now we're going to see some risk reduction measures and functional safety requirements applied on AGVs that helps create a safe product as well as prevent hazards while using the product. So these are examples of risk reduction measures coming from the ISO 3699 for driverless industrial trucks. We can find use safe speed monitor to select safety fields, use safe sensors to monitor wheel orientation, limit drastically the speed of AGV when scanners can't be active. You need also to think of the infrastructure, so mark on floors dangerous areas, use blue safety lights to announce that there is an AGV present. Other safety reduction measure, inform operators and visitors about the risk, use safety scanners to monitor protective fields, which sizes depending on the AGV speed and direction. So these are all examples of risk reduction measures that you could think of while performing your risk analysis. Another typical safety functions for driverless trucks, we can find braking systems control and monitoring that we use. We use the speed control and monitoring, for example, We can find avoid overspeed as a function, avoid the instability, assure that the personal detection field is consistent with actual track speed. Yeah, this is also an example for people who are coming for railway as well. Like we have this kind of safety function. We can find the load handler position, motion, emergency stop function, warning system. So these are all examples of typical safety functions that you can think of driverless trucks, and they are coming straight from the ISO 3691 for driverless industrial trucks. Here in this slide, we have an example of personal detection. We have an example of requirements on the scanners. You look on your architecture of your system. So this is a simplified architecture. And for example, you look also at the elements that could lead to the failure. Here we have sensors failures. You have to think, for example, failure to stop before collision with persons, and deep dive in the architectures and the failures that could be happening through the architecture. For example, here you have sensor fails to detect. We have the motor failures. In this aspect, you have to think also of safety mechanisms that you need to add, for example, for motor failure, so that you can still prevent the top event, which is failure to stop before collision. So for that, you need to think also to add technical requirements. And for that, you will need to deep dive in the system and perform the safety analysis in both hardware and software part of the system. So this is what we're going to be explaining the next phase, and it's going to be presented and explained by my colleague, Miriam Verschoor, that will present it to you in the next slide.
Yes. So now finally, so we have spent all the time in analysis, thinking about our product. So now it's time to actually start doing it, start designing it. So in the next slide, we see, as we've said earlier in the functional safety, is all about the process. So if you go to the next slide, Neiroza, yeah. We are trying to, with our process, to make sure that our product is safe. This is done not only by choosing the right components, but it's also the whole part of the process, which is important. And one of the processes which is often used in functional safety is the V model. Probably lots of you also have heard of this V model. It's the case for system engineering as well as for your hardware and software engineering. So if we go to the next slide, we can see a little bit more in detail the V model. The concept is that we can reduce all the risks, not all the risks, sorry. We can reduce risks for functional safety by having a proper process, a structurized process, starting from requirements, so thinking, analysis of what is needed, and then only start with the system design, a structure, have a well structure into separate components, and then start with implementation. And not to be forgotten, of course, something I will say in a few slides as well, the verification and validation afterwards. So this V model, it's also the case in hardware design. So as I'm not going to go into that much detail for the hardware design, I would like to stress just a few elements if you're lucky in your design to be able to choose, for instance, for off-the-shelf elements. It's important to make sure that those components are fit for the purpose that you are going to use them for. Here in an example for the personal detection, we are looking at sensors. There are lots of sensors on the market. Which one to choose, that depends on your application, on your analysis that you have made, and therefore also on the requirements you have defined. And as we mentioned earlier, those safety parameters. Not only that, also you have to look into the application you're looking for. Is it indoor or is it outdoor? You could have specified all the safety parameters you want and choose a very nice sensor. If that sensor is meant for indoor and you're using it outdoor, you are causing certain extra extra dangerous, so extra safety issues. In this case here, also I can show, so you see in the technical data of the most of some of component manufacturers for typical sensors or PLC, you will find if they are following also these standards, you will find those parameters back, such as the category or which performance level they fulfill. You can find it back. And then it's up to you to choose the right one according to your requirements and to the function you want to fulfill. So in let me show you next quiz. And Neiroza is going to launch it. So for instance, imagine you have to perform a function which is required to be a performance level D. Which of these two sensors would you use? Sensor N1 with those technical data or sensor 2?
We'll leave you 1 minute to try to think of what could be the possible answer to the quiz. I can see people answering. Yeah, most of them chose sensor 1.
Yes. So may I congratulate you? Yes, sensor 1. It's indeed one of the better choices to do. However, there are lots of other factors why you would be choosing some components, in this case sensors. There might also be cost factors and so on, and which was not really shown in here, also depending on the architecture you have in mind. It could be that you have two sensors which are redundant from each other, and you're building yourself some kind of an architecture with two independent sensors, and therefore making them more reliable by being combined. And therefore, sometimes it could be that you would be using two separate sensors from a lower performance level. But of course, if you were to use one, sensor 1 would be the better one, as it is able to fulfill the performance level D that you require. So after you have, so once you are doing your hardware design, but of course, most of these autonomous driving system are nothing without the software. So let's look at software design as well. Again, process is key here for safety. We are trying by making sure that our process is done properly to cover as much mistakes as we could be doing as much as possible. The process you follow, it also depends on the performance level that you require. So your effort you will spend into your software development and testing will be different depending on how reliable your system needs to be, how safe it is, what kind of risks your software would cause if it were not to be okay. So in a case of performance level E, you can imagine that you will be spending more effort into making sure that the safety is guaranteed compared to a performance level A. So I'm also going to say here I'm showing the typical V model for software design. Obviously, a lot of autonomous driving systems are starting to use more and more artificial intelligence, and for these there are some extra requirements which I'm not going to go here into details for. Yes, next slide. So for the software implementation, you have your safety related software. Be aware to not mix software related functions with safety related functions with non-safety related functions. What do you have in your safety related software? Typically you will have your monitoring, so how to make sure you have your diagnostic coverage. If you do it by software, you will be doing monitoring here. Also how to reach a certain safe state. It could be done also by software. These are examples of your safety related software. How to make sure you do not restart unintentionally or stop as you should be stopping, etc. This is your safety related software. If you are lucky, it can be that you have at your disposition from your manufacturer, for instance, for PLCs, you have a simplified code generation in like the example here below, where you are able to use certain predefined functions and blocks that you can assemble together. That makes your life easier, but doesn't mean that by assembling it and it was prepared by other, that it's all safe on its own. No, still you need proper implementation and proper testing of your software. So basically, and also no spaghetti code. In safety, it's very important to have a proper structure, and the more simple your code is, the less prone to errors it is. So next slides. On the other hand, in software, two very important items are the configurations and the parameterization, both of which you could have been doing a very good job in software implementation. You could actually also be doing very bad job by having a wrong configuration or parameterization of your software, resulting in risks which you want to avoid. It means that for software implementation, you need a proper process as well for software configuration management. One thing. Second thing, for your parameterization, it should only be allowed to be performed by trained personnel. It should always be very documented and always used with a verified tool. And these are very important. Let me give you an example for zone definition. Depending on how if you have an AMR and you are a designer, it could be that you allow your integrator who is implementing your product onto the company or industry within a logistics center where it has to be used, is allowed to change configurations, change parameterizations such as the zone. In this case, it is important that this cannot be changed in a way which would imply risks. So very important as to be trained personnel documented and verified tool, and no possible errors can come from there. Next slides. A very important part is verification and validation. And often we think, okay, it's at the end, No, it is not. So this graph here shows how verification and validation is going through your whole development. Verification on one hand, which is really looking into reviews of all the documents you are providing, reviews, did I write all the system requirements? Is it complete? Is it correct? Is it based on safety analysis? Did I design my product properly according to those requirements? Did I miss anything? Those are very important aspects that need to be looked at on one hand. On the other hand, also the validation. Did I actually, the implementation that I did, is it actually fulfilling what I was expecting it to? And by splitting it up in several sub, let's say, in unitary testing, component testing, integration testing, you are making sure that you have covered everything. And that's why the functional safety is all about the process, how you try to figure out that you have covered everything to make the product safe. Yes, next slide. An example of a test for driverless trucks. So the previous slide was about the generic idea. In ISO 3691 for driverless industrial trucks, there are even certain examples of tests that have to be performed. One of these tests, this is then a validation test once the product is already built, is to really, for detection of people in this case, and to do a test in, for instance, both direction of travels, whether the truck is able to detect certain people or objects. There are other types of tests, of course, dynamical tests, structural tests, stability tests. There are lots of safety tests that have to be performed, and depending on the requirements you have set. So now we have spent time in analyzing the product. We have done a theoretical design. We did our best to implement it in the way that we thought was correct and verify it. Of course, now it's time to actually produce it as it should. And in the production phase, it's important to have the typical quality norms in mind and to follow a good process as well, to have defined also where things can go wrong. You can have a perfect design if in production it is not assembled properly, your system will not perform as expected. But in this phase, typically also it's getting ready for the real world operation. And in that case, especially for driverless trucks and HEVs or AMR, you have to prepare your documentation as well to make sure you are compliant to the safety standards, among others, but also training of people and making sure also by the right documentation that in the next step people are able to assess, as I just mentioned for the hardware development. It's the same case for the complete system that you are selling. People have to be able to assess whether they are using your system in its right environment, and they can assess themselves the risk they are taking when they are using this product. And this is a preparation which is done in this production phase. But Neiroza will continue us from now, and she will explain also more into detail what is important to take into account now in here for the operation and next phases. Sorry, Neiroza, you are still on mute.
Thank you for notifying me. I hope everyone is listening now. We have seen how functional safety is implemented in analysis phase, how it is implemented in realization phase going to production. Now, the last phase that we're going to see is the exploitation phase, and we're going to see how functional safety it is implemented through both operation and maintenance and also the commissioning. And I will be giving you some examples to visualize in these two steps. So the first is operation and maintenance. And in here, we have inputs and outputs and objective of why we use it in operation and maintenance. So operation in maintenance we try to ensure that the functional safety is maintained at the specified level for the EEPE safety-related systems. We try to ensure that the technical requirements that were already specified in the previous phases that are provided in our operation and maintenance phase. So as a general input, you have the general operation and maintenance plans, and you have all your safety requirements in this general operation maintenance plans. You need to implement them in operation and maintenance phase by at the end to get the chronological documentation of the EEP safety system operation in the repair and maintenance. So this is a small example of an output that is the original instructions that is given to the people of maintenance and repair. In this document, we have in this original instructions information concerning the tracks and the system. We have information concerning the operation that should be played on the tracks and the system. We have all the informations on the routine service and the maintenance of the tracks and the system. We have the information about the operating and the operations that should be held in this phase. We have the information of the application of the operation, and you can find an example on the preparation. So here details for the floor, the ground conditions in which we should operate or maintain our products. So also in this, we have some of the safety requirements that we already defined them in the concept phase, in the design phase, that are in this instructional documentation. So what you need to remember is that documentation is the chronological documentation is also important for the assessments and also for future uses. Here as well in the commissioning phase, we have the inputs, which is the request for the commissioning. And also in these inputs, we have the functional safety requirements that were already defined and specified in the previous phases. We have our outputs, that we have achieved the functional safety during and after the commissioning phase. We deliver at the end the chronological documentation of the commissioning phase, and the objective of this is that we define the necessary procedures to ensure the functional safety. So here I will give you an example of the commissioning, because I can see that it's hard sometimes to visualize what we do in functional safety, what are the aspects that we need to take into account in these latest phases. So here for an example of the commissioning, the scenario here is a manufacturing plant that has a robot arm that reached the end of its operational life. So it is being replaced. the process that should be followed is to conduct a risk assessment to identify the potential hazards that are associated to shutting down and dismantling the robot. This includes evaluation, so evaluating the electrical, the mechanical, the software risks, and other aspects. For example, check that the power supply is safely isolated to prevent accidental startups during the commissioning. Think of deactivate the data backup and the software program. Ensure also that all the moving parts are securely immobilized, and don't forget, and others aspects that you need to check also, but don't forget that you need to document the entire decommissioning, which is essential for regulatory compliances and also for future references for future uses. So here, let's do a final quiz of this training, in which I will try to see if you can recall some of the important phases and steps of the functional safety process. So I will try to launch the quiz. And I will give you 1 minute to try to recall as far as we've been starting in our training, the first 3 activities that comes in your mind and that you think that you need to perform in functional safety process. So it's a multiple choice question, so feel free to answer. Yes, and also for those who, because I've seen in the chats, I've noticed that some of you don't have access to the polls. Sorry for the technical issue. You can also feel free to drop your answers on the chat. So you already have your supportive slides where you can see the options. Feel free to drop your answers on the chat also. So really think of the first 3 activities that you need at the very beginning. I can see people responding. That's good. Nice sign. Let's see on the chat also. Yeah, I think that 1 minute has finished. And the overall results, most of you got to recall the first steps: risk analysis and safety requirement specification, the system definition. These are definitely the first steps that you need to implement while in a functional safety process. So you need to have, as I said before, a system, a definition of a system. So you have your architecture, all your elements, you have your functions, you define your malfunctions. This will help you to define the risks, to analyze the risks that are related to these functions. And with the tools and the methods that we use, it will help you to have a complete specification of your safety requirements. So I can see that people did hardware, software design. Yes, also this is steps that you use them in the hardware and software design also. So the overall, I can see that more of you have guessed the correct answers. I need to congratulate you for your work, for your right guessings. Well done. Good job. I'm very proud of my audience today. So now we will close the quiz, our final assignment for this training. So you need to remember at the end of this training that the functional safety is implemented through phases. It's not implemented in the beginning, or we wait until the end, or in the middle of the life cycle of a product design, but it is implemented throughout all the process, the analysis phase, the realization, and the exploitation phase. And these are some of the key aspects of that. So we didn't deep dive into the details, but this is just the level of awareness. So at least you can recall some of these aspects when you have a product that you would like to design. We arrive to the closure of this training. We have seen the meaning of the functional safety. We have seen the objective and the importance of functional safety in the product design. We have seen the methods and the process of functional safety that goes both with the design life cycle, which are analysis phase, realization phase, exploitation phase, to go from just a simple product idea from concept phase to finally be able to deliver a robust, reliable, and safe product. I hope that now at this phase, you are able to understand the relevance of functional safety and that you can recall the functional safety process you need in your projects, as well as the safety parameters and methodologies used in order to assess and improve your product and process design. So these were our learning outcomes of this training. And now if you have any questions, I will be happy to answer them. So before we start the Q&A session, I would like you to take 2 minutes to answer the survey that I will send you now in the chat if you cannot be able to scan the QR code to access to it. So I put the link for you in the chat, or feel free to scan the QR code from the slides. Normally it works. Please take 2 minutes. And then we're gonna open the Q&A session. So meanwhile, let's open the Q&A session. Yeah, can you see if we have any questions? Please feel free if you have new questions for now we can answer. Or any comments you want to put on your chat also. Or was anything that wasn't clear? Or maybe everything was clear enough for you?
So there is a question, do you know when the ISO 13849 is updated to do the new machinery regulation? There have been recently an update of the 13849 in 2023. It already holds some items which are related to things that are also in the new machinery regulations. For instance, in the 13849, they shortly mention the fact that you can start using AI also in your safety critical systems, but that there are extra requirements for that. The new machinery regulation is also introducing some concepts about the fact of using AI, which before that was not done in safety. Is it going to be updated? When exactly it's newly going to be updated, I cannot say.
Yes, and also for now it is on 2023 that we have. For now, the updated version is on the year of 2023. Yeah, I can see a comment. It was a lot to take in such a short time. I must agree. But at least we try to make a generic visualization of functional safety. Yeah, and you must be sure that there are more detailed in functional safety process. So these are really like the overall generics of functional safety. And if you want to understand more and more in depth about each step, like you have our contacts on the slides, feel free to contact us at any time if you need further information. Yeah, or maybe further trainings more detailed in each aspects of functional safety. Yeah, I have a teaser that I can share. I will put it on the chat also. But if you want more information, you can just directly contact us. So still have 5 more minutes. If you have any additional questions, and then I suggest to close our webinar for today.
So we have one more question about the certification process for a D or E product. Not sure what do you mean exactly. So typically in a certification process, especially for T or E, meaning it's a higher risk, you might need to involve certification bodies. If that's the question where you were interested in. In Europe, there are several certification bodies that will help you with your certification. Of course, they are external. They are more costly than if you would be able to do it in-house. There are certification bodies such as TÜV, for instance. There are several instances, but there are many more. Depending on the country you live in and what is reachable for you. Does this answer your question? Yes.
Yeah. Yeah, there are certification bodies, but they differ from any domain. Like the ones in the railways are not the same as in the robotics, are not as the same as in automotive vehicles. So it depends, and there are plenty, I know, for machinery, for example. Yeah.
They will typically check whether you fulfill the standards or, most importantly, also the regulations of the market you want to be in.
Does anyone have any additional question, maybe commentary? Or did everyone completed the survey that I sent? If yes, say yes on the chat so that we can see. Yes, okay. I think there are no more questions. So I would like to thank you again for having reserved this time for attending our training. So as I said, it's training for functional safety for autonomous guided systems, and the level of this training was awareness, mostly for beginners and for people who are really willing to know a little bit about functional safety and also some of functional safety application on machinery and robotic systems. I hope that you enjoyed the training, the assignments, and the small quizzes that we did through this training. And thank you for your presence again. You have on the slide our contact if you are interested, maybe to support you in implementing your functional safety during your product life cycle, or any additional questions that you have maybe after this session. Feel free to contact us. Thank you very much, and I suggest to close the session for and have a nice rest of the day. So goodbye, everyone.